Okay, so we're going to look at a combination circuit, and first we're going to draw the circuit and look at its components, and then we'll look at a VIR chart to examine the changes or drop in voltage, the current, and the equivalent resistance throughout the circuit. Alright, suppose we have a voltage supply, and we'll draw that here. There's our positive, and here's our negative, and from that, let's say we have a circuit that looks like this, and let's start by putting, that's one resistor and another, and let's do 6 in all. And what makes this a combination circuit is that, as you can see, there are a number of resistors in series, and they are in parallel with each other. So when you have a combination of series and parallel circuits, you have what we call a combination circuit. Alright, so let's assume that we have, in fact, let's put one more in here, and we'll make it a 7th resistor. Let's make that look like a resistor. It's not a very good job. And we'll label that, hey, where'd you go? We'll label that R7, so there's resistor 7, and now let's suppose that we have a voltage source that is, we'll give it a value of, what do we decide on, 12 volts. So here's a 12 volt voltage supply, and now we're going to write down each of the resistors, number of ohms, their resistance, and we'll say this one is 15 ohms. There's omega. And let me finish this here so you don't have to listen. Okay, so here are all the resistors with the number of ohms of resistance. So we have a R1 has 15 ohms, and that's like a small incandescent light, a hobby light. R2 is maybe a holiday light bulb, 20 ohms. R3 is an 85 ohm motor, and R4 is another holiday light. R5, another motor. R6, another holiday light. R4 was an incandescent light. And at 150 ohms, R7 is a piezoelectric buzzer. And again, we have a 12 volt battery supply. So let's create a VIR chart to show the breakdown of all this information and how we can figure out all of these values. And this is one of those things where it's not the final product that is important, it's the process that we use to get there. So let me make sure we have enough space. So I've entered in all of the given values. That was that the resistance of each of these resistors is 15, 20, 85, 15, 85, 20, and 150 ohms respectively. I put my voltage, my current, and my resistance at the top, and included my units so I don't have to include units throughout. And here are all of my resistors in order, and my total column, which will come this way. And you'll notice I left some room over here, and that is for the fact that these two, and these two resistors are pairs of resistors in series with each other, but parallel to each of the other branches of the circuit, for a total of 5 branches. Rather 4 branches. So now I'm going to go about adding the resistance of each series pair and put that total here, because when you have resistors in series, the rule is that you simply add them linearly, and that gives you the total resistance. Now the rule is, when you're adding resistance of resistors in parallel, that you don't add them linearly like you did when they were in series, but you add their reciprocals. So what we'll do is we'll add 1/35 plus 1/100th plus 1 over 105 plus 1 over 150. We'll add those and then take the reciprocal of that answer to get the final equivalent resistance for the entire circuit. So the way I would type that into my calculator would show that I have 35 ohms of resistance, and we'll take that to the -1. That's a -1. We'll add that to the reciprocal of the next resistor, which is 100, close parentheses, to the -1, plus the next resistor, 105 to the negative 1 plus 150 to the negative 1. Then we'll close the parentheses one more time, and we'll take that entire expression to the negative 1 so that it takes the reciprocal of the sum of the reciprocals. I'll say that again because that's the rule. You want to take the reciprocal of the sum of the reciprocal. So the total, that is the sum of the reciprocal of the sum of the reciprocals, is 18.26 ohms of total resistance through the entire circuit. Now what we're going to do is use Ohm's law to figure out the total current through the entire system. Using Ohm's law, which says that current is equal to voltage divided by resistance, we will take the total voltage of 12 volts and divide it by 18.26 ohms of resistance and get a total current of 0.657. Now, we also know that this is the current through the entire circuit, and there's going to be some rules that apply to current through series and parallel circuits, as well as voltage through series and parallel circuits. And those rules are as follows. When it comes to voltage, we know that each branch is going to get 12 volts. We know R7 is on its own branch, so that gets all 12 volts. And then I'm going to put a little 12 right here to remind me that R5 and 6, that branch gets 12 volts. R3 and 4 get 12 volts that they share. And 12 volts goes to the first branch, which has resistors 1 and 2. Now, again using Ohm's law, we're going to say that this voltage times, voltage of 12 volts divided by the resistance to that total, or that to that branch, 35 ohms, is going to give us the number 0.343 amps. 343. I'm not sure that looks like it. Amps of current, and the rule is that in series, the entire series circuit gets the same current, so that once again we're going to write 0.340, or 3 rather. And now I went ahead and completed the same process again. I took 12 volts and divided by the total resistance to that branch of 100 ohms and got 0.120, and know that each resistor gets the same current because it's on the same line. And R5 and 6 get 12 volts, and with 105 ohms of resistance, each resistor gets 0.114 amps of current. And lastly, R7 on its own branch with all 12 volts divided by all 150 ohms of resistance gives us 0.080 amps of current. Something tells me this R7, this piezoelectric buzzer, is probably not going to make any sound. Now, last but not least, we're going to find the voltage drop, the drop in electrical pressure across each of these resistors. We know R7 drops 12 volts across that one resistor because it's the only one on that branch, but the rest of these have different drops in voltage because there's some resistors in series. So what that's going to look like is we want to find the voltage. So in order to find the voltage, we're going to multiply current times resistance. So we're just going to take the current in through each resistor and multiply it by the resistance, and that will give us the voltage. So in other words, we'll take 0.343 amps and multiply it by 15 ohms and get the number 5.15 volts dropped across resistor 1. We notice we can now ignore the 12 volts that are here because that's the voltage to the entire branch. Now we're looking at the voltage to individual resistors, and 0.86 volts, and you'll notice that if I add the voltage here and here, I'll get roughly 12 volts, and only different because of some rounding. So I'm going to go ahead and calculate the rest of the voltage drops. So you can see that in each case, when we add the voltage drop through the two resistors on each branch, that they each total to 12 or thereabouts. And we'll also notice that if we take the current through each branch and we add them up, we'll get the total current of 0.657 amps. So there you have it. This is the combination circuit and the VIR chart for that combination circuit. Here's the original circuit, the 12 volts through the entire thing. And so this circuit represents several resistors in series and in parallel, making a combination circuit. And to review quickly the order of steps, first we filled in everything that we knew that we were given in our circuit diagram. Then we took the equivalent resistance in each branch and found that, which I put out here to the far right. Then I added their reciprocals and took the reciprocal of that and got 18.26 ohms. Then, using that, it seems to have disappeared, I got the total resistance of current of 0.657. That has since disappeared. Then, using Ohm's law, I did that. Then I knew that 12 volts were being applied to the resistance in each of the individual branches, and so 12 divided by the resistance in each branch gave me the respective currents through each branch. And then once again, using Ohm's law, this time multiplying current times resistance through each resistor, I found the individual voltage drop across each resistor. Well, there you have it, folks. After almost 12 minutes, I hope this was helpful, and keep studying.